So good morning students, I am Prabhu Bain Bharat, Assistant Professor Department of CSE, BLDCT, Bijapur. So in this lecture we shall discuss about random number generation techniques. So here I am going to discuss mixed congruential method, multiplicative congruential method, test for random numbers, that is frequency test. So techniques for random number generation. The following are the most widely used techniques for random number generation. So linear congruential method, combined linear congruential method, and random number streams. So in this video we are going to discuss about linear congruential method and different random number testing techniques. So linear congruential method, this method is proposed by Lehmer in 1951 and produces a sequence of the random numbers x1, x2 between 0 to m minus 1 by following recursive relationship. So this equation is used to produce sequence of random integers x1, x2 so on 0 to m minus 1. So here a is multiplier, xi is seed, that is initial value, and c is increment parameter and m is modulus. So depends upon the value of c. Again this method is divided into two types. If c value is not equal to 0, then that is called as mixed congruential method. If c value is 0, then that is known as multiplicative congruential method. See, one important thing is the selection of the values for a, c and m and x0 drastically affect the statistical properties and cycle length, and the sequence of random numbers between 0 to 1 can be generated by the following equation, that is Ri equal to xi divided by m, where I equal to 1, 2, 3 so on. So let us consider a problem statement. Use linear congruential method to generate a sequence of random numbers where x0 is 27, a is 17 and c is 43 and m is what here 100. So here the parameter value c is given. That's why we will use mixed congruential method for generating a sequence of random integers between 0 to m minus 1, and we can also generate a sequence of random numbers between 0 to 1. So this formula is used to generate a sequence of the random numbers between 0 to 1. This equation is used to generate a sequence of random numbers between 0 to m minus 1, it is used to generate, and 0 to 1 random numbers can be generated by using this equation. So here initial value of x0 is considered as 27. So the value of a is 17, so 27 into 27 plus 43 mod 100. So x1 is what here 2. The equivalent random number is generated by substituting values in this particular equation, that is xi is 2, m is 100, so 2 divided by 100 equal to 0.02. So this is what here r1 random number. The x2 random integer is calculated by using the r1 random integer, that is 17 into 2 plus 43 mod 100. So we get the x2 random integer as a 77, and the equivalent random number is 77 divided by 100 equal to 0.77, and x3 is calculated as 17 into the x2 random number plus 43 mod 100. So x3 random integer is 52, and equivalent random number, that is r3 equal to 52 divided by 100. this is equal to 0.52. So we will calculate the random integers, that is x4, x5, x6, x7, x8, x9, so on up to 99, and equivalent random integer, random number, by using this particular equation. So let us consider second problem statement. Generate 5 numbers of a random sequence using multiplicative congruential method with x naught equal to 2, a equal to 13, and m equal to 64. So in this problem statement, the parameter value c is not given, hence we will consider the value of c is 0. So therefore we will use the multiplicative congruential method. The equation is reframed as follows, that is xi plus 1 equal to a xi, the value of c is inserted as what here, 0. So this becomes a xi mod 100. So we consider the seed value as 2. So first random integer is calculated as follows. So 13 into 2 mod 64, that is 26. The equivalent random number, that is 26 divided by 64, equal to 0.40. The x2 is calculated by using x1 random number, that is 13 into 26 mod 64, that is 18. The equivalent random number is R2 equal to 18 divided by 64 equal to 0.28. So in this problem statement, they have asked us to find out 5 random numbers, right? So 2 random numbers we have computed here. So we will continue till to calculate 5 random numbers. So x3 is computed, random integer, that is 42. This is equivalent random number. x4 random integer is 34, its equivalent random number is 53. So x5 is calculated by using x4th random number, that is 34, 13 into 34 mod 64, and this is x5 random number, that is 5th random number integer, this is 5th random number. So on we will calculate the random number till x8, right? So according to problem statement, they have asked us to compute or generate a random numbers till x5, but we have continued till x8 here. See, here we have listed all the generated random numbers in a sequence. See, one thing you can observe is the random numbers from x0 to x7 are unique here. The same number is not repeated here. See, after x7, so after x7 means x8th number is again repeated here. Suppose if we compute the next random number, that is x9, definitely this would be what here, that is x1 random number, 26 will be repeated. See what happening here, after some time the same random numbers started repeating. So the random numbers which are not repeated until some extent, that particular length is called as what here, cycle length or the period of the generator. So consider following problem statements and do generate a sequence of the random numbers, right? So in this problem statement you have to use mixed congruential method and you have to generate a sequence of the random numbers. See, here they haven't asked how many random numbers you have to generate. So you have to generate a random numbers from x0 to m minus 1. See, here you have to consider multiplicative congruential method and you have to generate a sequence of the random numbers. right? And generate a sequence of the random numbers and identify maximum period here. So the maximum period is nothing but the length of the cycle. So up to how many numbers the same numbers will be started repeating, that you have to identify. See, initially you have to consider the value of x naught equal to 1 and a equal to 13 and m equal to 2 raised to 6, and you have to go on generating a sequence of random numbers, and you have to identify what is the length of the generator, right? See, after how many numbers the same random numbers will be started repeating, that you have to identify. So again, in next step, what you have to do, you have to consider value of x naught as a 3, and you have to consider a value 13, m value 2 raised to 6, and you have to generate a sequence of the random numbers, and you have to identify what is the maximum period of this particular generator, right? So on, you have to find a sequence of the random numbers, or you have to generate a sequence of the random numbers and respective cycle length, that is maximum period, by considering x naught equal to 1, x naught equal to 3 and x naught equal to 4, by keeping the value of a is 13, m equal to 2 raised to 6. See, one more problem statement has been given here. Generate a sequence of 10 random integers. So usually in question paper they will ask you to generate a particular set of the random numbers. So they ask you to generate how many numbers you have to produce, right? So here they are asking you to generate 10 random numbers by considering x naught equal to 63, a equal to 19 and c equal to 0 and m equal to 10 raised to 2. So in this section we shall discuss the tests for random numbers. The desired properties of the random numbers are uniformity and independence. So we can use different tests to check whether the generated random numbers will satisfy the property of uniformity or independence, right? So those tests are categorized into two groups. It depends upon what here the ideal properties of the randomness. So we will conduct a different types of test to check for the uniformity, and also we use different test for independence. So the whatever the test which we use for checking the uniformity of the sequence of the numbers, those test is called as what here, frequency test, and autocorrelation test is used for checking the independence property, right? First we'll see frequency test. So we have two frequency test which we will discuss in this video. So that is Kolmogorov-Smirnov test. It is also called as KS test and chi-square test here. So these two tests are used to compare the distribution of set of the numbers generated to a uniform distribution. So whatever the numbers which are generated from a particular random number generator technique, so all those numbers are compared for the uniformity distribution, right? So in case of autocorrelation test, this test is conducted to check the correlation between the numbers and compare the sample correlation to the expected correlation. So what is a means the correlation of sample and what is the expected correlation, so that is cross verified here. So let us first discuss about uniformity test. Okay, so in this test what we do, we will use the following hypothesis. So H naught is nothing but null hypothesis. It defines Ri means every random number is uniformly distributed between 0, 1, and H1 is, this hypothesis indicates the random number Ri not uniformly distributed between 0, 1. See, the null hypothesis, that is H naught, reads that the numbers are distributed uniformly on the interval 0 to 1. So failure to reject null hypothesis means that evidence of non-uniformity has been detected by the particular test here. So these two hypotheses we will consider. And one more parameter we will consider, that is level of the significance. So for each test, a level of the significance, that is alpha, must be stated. The alpha is defined as the probability of rejecting the null hypothesis when the null hypothesis is true. So when the null hypothesis is true, what is the probability of rejecting that hypothesis? This is defined by what here? Level of the significance. This is calculated as the probability of reject null hypothesis divided by null hypothesis true here. So let us see how the test will be conducted. So here first we shall discuss about Kolmogorov-Smirnov test. So this is also called as KS test. So in this test, it compares the continuous CDF cumulative distribution function, that is f of x of a uniform distribution, with empirical cumulative distribution function, that is Sn of x of the sample of n observation. So what it will do, it will compare the continuous CDF of uniform distribution with empirical CDF, that is Sn of x of the sample of n observations. So whatever the empirical test is conducted on n observation, that is compared with what here? The theoretical uniform distribution CDF. So this is CDF of uniform distribution and this is empirical distribution CDF. So here the CDF of empirical distribution is compared with what here? Uniform distribution. So here Sn of x should become better approximation to f of x, provided the null hypothesis is true. So if the null hypothesis is true, it means that the empirical test cumulative distribution function is approximated to what here? The continuous CDF of a uniform distribution. So we will calculate what here? The value of d. So the d is nothing but largest absolute deviation between f of x and Sn of x over the range of random numbers. So depends upon the value of d, we will take a decision whether the sample of n observations are uniformly distributed between 0, 1 or not. So the following are the steps for the case test for testing against the uniform distribution, that is CDF. So the first step is what here? Arrange the data from smallest to largest, that is the first number R1 is less than or equal to R2, R2 is less than or equal to R3, so on, less than or equal to what here? Rn. And first we will compute what here? In a second step, d plus. The d plus is nothing but largest deviation of Sn of x above f of x. So that is calculated. So d plus is calculated as follows by using this equation. So where I divided by n is nothing but empirical distribution, that is Sn of x. Sn of x equal to number of random numbers which are less than or equal to x divided by what here, n. So after calculating Sn of x for all the observations, we will find out what here, d plus. After computation of d plus, we will compute what here, d minus. After this, in a step 3, we will identify the maximum, the largest standard deviation between uniform distribution and empirical distribution. And in a fourth step, we will locate the critical value for the specified level of the significance alpha and given sample size n. And in fifth step, we will compare the statistical value with what here, the critical value. If the statistical value is less than the critical value, we consider that the given random numbers are uniformly distributed between 0 to 1, means it is failing to reject the null hypothesis, means we are accepting that all the given numbers, random numbers, are distributed between 0 to 1. So let us solve the problem by applying this procedure. So the problem statement is, suppose 5 numbers are given. So these are the 5 random numbers. So n is how much here? The value of n is 5 here. N is 5 here. Okay. So test for the uniformity using KS test with level of significance alpha is equal to 0.05. Right. So we have to consider alpha is equal to 0.05, and we have to test whether all these random numbers are uniformly distributed between 0 to 1 or not. So in first step, what we do, we will arrange all these numbers in ascending order. In the second step, we will calculate d plus. So before we compute d plus, we will compute what here, the empirical distribution, that is I divided by n. So I divided by n equal to number of random numbers which are less than or equal to x. So here x will be what here, the random number, random integer, right. So first value, that is I divided by n equal to, so 1. 1 means what here, we will consider first random integer, first random number, that is 0.05, and we will check how many numbers are present in this list which are less than or equal to 0.05. See, this is the only one number, that is 0.05, which is not less than 0.05, but it is equal. So only one number is present in the list, so that 1 divided by, what is the value of n? 5. So we get 0.20. So we consider second number, that is 0.14, and we will identify total how many random numbers which are less than or equal to 0.14. So total 2 numbers. So this number is what here, less than, this is one number, and this number is not less than but equal to 0.14. So but this number, all these numbers are what here, greater than 0.14. So hence 2 numbers are present in this list which are less than or equal to 0.14. So that's why 2 divided by 5. So we get 0.40, and we calculate it for third number. So this is 0.16, 0.08, and fifth number 1.0. So we will construct a table in this format. Ri is nothing but what here, list of the given random numbers, and this is what here, empirical distribution, so of respective random numbers, and we calculate d plus, right, by applying what here, this particular formula, that is Ri divided by n minus Ri, nothing but the first value is what here, 20 minus 0.05. So all these values are calculated. So next we will calculate what here, di. So Ri minus 1 divided by n. So Ri means what here, I value is what here, 1. So first random number, that is 0.05. So what is the value of I? 1 minus 1 divided by 5, this is 0.05. Next I value is what here? 2. Second random number we will take, so that is 0.14 minus I value is how much here? 2 minus 1 divided by 5, this is 0.06. So we will calculate di value for all the random numbers. So in third step what we do, we will identify the maximum of say d plus and d minus, right? So see here 26, we have highlighted here 26 and 21, 0.26, 0.21. So the maximum of these two values is what here? 0.26. that is what here the test value, and we will obtain the d alpha from the table. So at the end of the book they have given a table critical value for the uniform distribution. From that table we will note down this particular value, right? So this is a table. See what is the size of the data? That is n equal to how much here? 5. And what is the alpha value? 0.05. So when the size of the data is 5, alpha value is 0.05. this is a value, critical value. So this value we will take and compare with what here? D value. So the value of D is what here? 0.26, which is less than 0.565. Hence we conclude that whatever these random numbers which are given, all these random numbers are uniformly distributed between 0 to 1. So the null hypothesis is accepted. And this graph shows the comparison between the uniform distribution with what here? The empirical distribution. So we will consider second problem. The sequence of the random numbers are given. So this is 0.11, 0.68. Use KS test with alpha is equal to 0.05. Test whether the hypothesis that the numbers uniformly distributed on the interval 0, 1 can be rejected. So the first step is what here? Arrange all the random numbers in ascending order. So this is done here, and compute d plus for all the random numbers, compute d minus for all the random numbers, and find the maximum of d plus and d minus, that is test value. So compare this with what here? Critical value. So here the test value is less than or equal to critical value. This is obtained from the table. Hence whatever these random numbers which are given are all distributed between 0 to 1. So next we shall discuss about chi-square test. So the chi-square test uses the sample statistic as shown below. So that is summation I to 1 to n, where n is the number of the classes, y is the observed number in the ith class, and ei is expected number in the ith class, and ei is calculated by what here? Ei equal to n divided by capital N divided by small n, where n is the total number of the observations. So this particular test is used for the sequence of the random numbers where the size is what here? Greater than or equal to 50. At least the sample size should be what here? Greater than or equal to 50 here. So let us see how chi-square test is done. See, consider a problem statement. Assume 100 numbers are distributed between 0, 1. So those 100 numbers are not listed here, right? So they have considered total how many numbers here? 100 numbers which are distributed between 0 to 1, and the number of the samples observed in each interval is given in the table. So consider 10 intervals of equal length, and the level of significance is what here, 0.05, and test whether all those 100 numbers are uniformly distributed or not. See here, total size of n is what here, 100. The size of the data is what here, 100. Okay, and how many classes or intervals they are considering here? 10 intervals. So 10 intervals means these 100 numbers are divided into what here, 10 say intervals. So the first interval is from 1 to 10, second interval is what here, 11 to 20, so third interval is what here, 1 to 21 to 30, so on, and last interval is 91 to say 100. Okay, see in this problem statement they have given how many numbers are observed in each interval. Okay, in first interval, that is 1 to 10, 10 numbers they have observed, so which are falling between what here, 1 to 10 out of 100 numbers, and 9 numbers are falling between 11 to 20 out of 100 numbers. That is the meaning here. So this information is listed depends upon what here, the observation of the 100 numbers. Okay, and what we do, we will first calculate what is the expected number of the expected numbers in each interval. So that is calculated by what here, this particular equation. So that is EI equal to, so 100 divided by what here, what is the size of n, capital N, 100. How many classes? 10 classes. That is n, small n is what here, 10. So that is 10 ones are 10 tens are, means in each class how much we are expecting, 10 values, but how much is observed? In first interval they have observed 10 values. In a second observation, in a second interval, how many values are falling? 9, but what is expected? 10. So what we do, so we will write down the intervals in this manner. So this is first interval between 1 to say 10, second interval is between what here, say 11 to 21, so on, and last interval is what here, say 91 to say 100. Okay, so here what is observed values? So go on writing the observed values here. That is, according to observation, 10 values are present in first interval, 9 values are present in second interval, 5 values are present in third interval, so on. 14 values are present from 100 data, 100 sample size for the last interval. But how much we are expecting here? In each interval we are expecting 10 10 10 10 values. So like this we have written. So first what we do, we will calculate OY minus EI according to this formula. That is, only this much we will calculate here, OY minus EI, that is observed in ith class, particular class, and expected in that ith class here. So that is 10 minus 10 is equal to what here, 0, 9 minus 10 is equal to what here, minus 1, 5 minus 10 is equal to what here, minus 5, so on we will calculate. So next what we do, we will calculate this particular segment, that is OI minus EI bracket square. So that is OI minus EI bracket square. So 0 bracket square is what here, 0, 1 bracket square is 1, minus 5 bracket square is 25, so on we will calculate. So next what we do, we will calculate OI minus EI bracket square divided by EI. So this is OI minus EI bracket square divided by EI. So what is the expected value of this particular interval? That is 10. So 0 divided by 10 is what here, 0. So 1 divided by 10 is 0.1. 25 divided by 10 is what here? 2.5. So on we will calculate for all the intervals. So after that, summation I to I equal to 1 to n. So we will add all these values. So we get 11.2. So this is what here the computed value. So this value is compared with the critical value. So the critical value is nothing but chi-square, the level of significance 0.05 comma 9 here. So why we have taken 9 means, so it is depends upon what here? The chi-square distribution with n minus 1 degree of the freedom. So n minus 1 means what here? What is the value of n? 10 minus 1 means what here? 9. So this value is obtained. This value is obtained from the table. So the table A6, so which is present in last page of the book. So there you have to find what here? 9th value. What is the level of significance? 0.05. So we get what here? 16.9. So this value is compared with what here? Our computed value. So our computed value is what here? Less than the critical value. Hence we say that all those 100 numbers are what here? Uniformly distributed between 0 comma 1. Yes. So next let us consider one more example. So use chi-square test with alpha is equal to 0.05. Test for whether the data shown below. So whatever this data is given now, you have to test this data whether all these random numbers are uniformly distributed between 0 to 1 or not. So all these random numbers are between 0 to 1. So you have to test whether these random numbers are distributed uniformly or not between 0 to 1. So what they are asking you, they have asked you to consider 10 intervals of equal length, right? And the first interval is what here? 0 to 0.1. Second interval is 0.1 to 0.2, so on, and the last interval is 0.9 to 1.0. And this is what here the critical value you have to consider. So first what we do, this is a equation for chi-square test, and first we will calculate what here? What is the expected value in each interval. So total how many random numbers are there? So if you count, this is total random numbers are 100. So 100 divided by 10. So nothing but what here? This is what here expected. So in each interval we expect how many random numbers? 10. So what we do? So first interval, second interval. So the first interval is what here? 0.01 to 0.10. The second interval is 0.11 to 0.20, so on. So in a first interval, how many values are expected? 10, 10, 10, right? In each interval we expect 10 values. And suppose if we observe, if we look at all this data in first interval, that is between 0.01 to 0.10, how many values are present here? So according to our observation, so we can find 8 values, but expected is how much here? 10. In second interval we are expecting 10, but how much we observe? 8. For third interval we observe 10. The expected is also what here? 10. In fourth interval we can only observe 9, means the 9 numbers. So out of 100, the 9 numbers which are between what here? Between the fourth interval, the range associated to fourth interval. So like this all these values will be taken. So next what we do, we calculate OI minus EI and OI minus EI bracket square, OI minus EI bracket square divided by EI, and all these values will be added. So we will get 3.4, and this 3.4 value is compared with what here, the critical value. So the 3.4 is what here, less than the critical value, hence the null hypothesis is what here, accepted. So we don't have sufficient evidence to reject it. So we can say that all these random numbers which are generated through some of the random number generator scheme, so all these are uniformly distributed between 0 to 1. So in summary, the Kolmogorov-Smirnov test and chi-square test are acceptable for testing the uniformity of the sample of the data, provided that the sample size is large. However, Kolmogorov-Smirnov test is the most powerful than the chi-square test, and Kolmogorov-Smirnov test can be applied to small size data, that is, the sample size is small. If the sample size is greater than 50, then we have to use what here, chi-square test. Thank you. Subscribe to my channel, YouTube channel, for more videos on system modeling and simulation and programming subject videos. Thank you.